So in chapter 1, I introduced differential and integral calculus. In chapter 2, we are going to begin by actually getting our hands dirty. That's like in a mathematical sense, getting our hands dirty. We'll actually find derivatives of functions. So I've already defined the derivative of a function. It's like the instantaneous ratio of change in the function to the change in the independent variable. And if your function was, for example, fx equal to x squared, and I said, what is the derivative of it at, let's say, x equal to 3, then what you could do is you could say, okay, at x equal to 3, the function value is 3 squared, that is 9. And let's just perturb the independent variable a bit. So let's change it from 3 to 3.01. So if you do that, the function is going to change to approximately 9.06. So then you look at the ratio of change in the function, which is 0.06, to the change in the independent variable, that is x. So that changed from 3 to 3.01. So that change was 0.01. And you take the ratio, and the ratio is 6. So you can say that at x equal to 3, the derivative is about 6. Now, that's one way to do it, and that's the numerical way to find derivatives. But what we would really like is a closed form solution. So what's a closed form solution? A closed form solution would be itself some function of x, which we can compute directly instead of having to do these little perturbations and so on. So we want the derivative function for fx equal to x squared. And the way we do it is we say, okay, suppose now, by definition, that is equal to the change in f by the change in x. And what is the change in f by the change in x? Well, if x changed from x plus delta x, then f would change to x plus delta x squared. And the change in f would be minus the initial value of f, which was only x squared. So the change in f would be the numerator here, f plus delta x whole square minus x squared. Okay? And the change in x would simply be the new value of x, which is x plus delta x, minus x, so that's just delta x. Now, what is exactly delta x? Delta x is the representation for change in something. So delta f is the change in f, and delta x is the change in x. Now, if you were to expand this using the binomial theorem, then x plus delta x whole square becomes x squared plus 2x delta x plus delta x squared minus x squared, this minus x squared, divided by delta x. Okay, so this amount is the ratio of change in the function f and the change in the x. Now this change in function f by change in function x is not yet the derivative. The derivative actually by definition is when these two changes are infinitely small. Okay, so the derivative is defined as delta f by delta x as delta x tends to 0, and that's a concept in calculus that of infinitely small changes. So in the first chapter, I had given you the intuition for derivatives as the ratio of change in a function to the change in the independent variable. For example, the change in distance to the change in time, and which you call speed, you call the derivative speed. Now formally in mathematics, it is the derivative is defined as the change in the function delta f divided by the change in the independent variable x as the change in the independent variable, that is delta x, tends to 0. So derivative is defined as this, and that then is represented as df by dx. Now this derivative for f equal to x squared becomes equal to, in the numerator we expanded the binomial and then we had a x square and then you had a minus x square, so the plus x square and minus x square cancel out and they leave 2x delta x plus delta x squared divided by delta x. Now this delta x cancels out with this one, and then from here the x square goes away, so you are left with 2x plus delta x as delta x tends to 0, and then this is the, so you say that it is equal to this as this delta x approaches the limit 0, and then you say that you can ignore this delta x because it is approaching 0, so all you have left is 2x. So the derivative df by dx equals 2x. Now I seem to have done something a bit tricky here. Firstly, I said delta x is not equal to 0, and that's why I was able to divide both the numerator and the denominator by delta x. So I said delta x is not equal to 0, so I'm allowed to divide by it, because in mathematics you know that division 0 by 0 is a no-no. You can't do that. So I did that, and because I said, well, it's not 0. And then I said, well, it is so close to 0 that I can actually ignore it and put the equality sign and say this is just equal to 2x. So I'm just having it both ways. I, on one hand, say delta x is not 0, so I can divide by it, and on the other hand, I say, well, it's so close to 0, I can ignore it and put the equality sign. And this is a very fundamental thing in calculus. It's the issue of infinitesimals. And for at least 1,000 years, mathematicians kind of thought about it and weren't sure about it, and there was, for some time, it was not a respectable idea. And even like people like, Karl Marx, who wrote a paper about it. And not that, that paper did not really advance mathematical thinking anyway. However, this idea is correct. This is correct as long as the axioms that you start with make these correct. So the mathematicians had to come up with the correct axioms to make this correct. And of course they did come up with it, and now it's not a controversial idea. It is in fact fundamental to differential calculus and also to integral calculus, because in integral calculus also the idea of infinitesimals is very important. For example, when you had the sphere and you are saying that the volume of one of the enclosing hollow spheres equaled dr into the surface area, that was assuming that the surface area of the outside and the inside were the same, and that of course is not true for a hollow sphere. The inside surface area is a bit less than the outside surface area. However, when the thickness of it, that is dr, approaches 0, then the integral does actually equal, and not approximate, but equal 4/3 pi r cube. And again, that happens, and that is correct because of the axioms that integral calculus was set up with. Okay, so now this was the method of first principles, which enabled us to find the derivative function for fx equal to x squared. And now, if I tell you, okay, what was the derivative of fx equal to x squared at x equal to 3, you don't have to like do these perturbations, like let's go from 3 to 3.01 and see how much the function changes and how much the independent variable has changed and take the ratio. You don't have to do that. You can just simply say, oh, that will be 2 into 3, that's 6. So this is a closed form solution. That's the advantage of it. You can get the answer immediately. You don't have to do it numerically. Okay, so what about finding the closed form solution of another function, again from first principles? And here, let's say, what if like fx was equal to x to the power n? And the binomial for x to the power n, when you have the independent variable changing from x to x plus delta x, the binomial expansion of this would give xn plus the second term would be n xn to the power n minus 1 into delta x, and then there would be higher order terms of delta x. Now the first term xn will cancel out with this xn, and so what you will have is the second term, which was n x to the power n minus 1 into delta x, and then higher order terms of delta x. Now once again, you can ignore the higher order terms of delta x as delta x approaches 0, because in the numerator you would have this quantity and then delta x and this delta x would cancel and it will leave you n x to the power n minus 1, and then there would also be some higher order terms of delta x, and as long as the power of the delta x term is greater than 0, as delta x approaches 0, that term is also going to approach 0. So from first principles, the derivative of x to the power n, which is represented by dxn by dx, equals n x to the power n minus 1. So similarly, we can find other derivatives using first principles, and then we can find still more derivatives using these derivatives by applying rules, for example, the chain rule. And we shall see a few examples of that. The next derivative that we will find using first principles will be the derivative of log x, that's ln x. So again, what you say is that x changes from x plus delta x. So this is the final value of the function, ln x plus delta x. The initial value was ln x, so you subtract that, and that you divide by the change in the function x. Now ln a minus ln b equals ln of a divided by b. So this x comes in here and you divide by it. So what you get for the numerator is log of x divided by x, that is 1, plus delta x divided by x. So log of this quantity, 1 plus delta x by x. Now this quantity delta x by x, as x tends to 0, is a very small quantity. And for a very small quantity, the log of 1 plus that small quantity is approximated to simply that small quantity. So this log of 1 plus delta x by x simply becomes delta x by x, and the derivative becomes delta x by x divided by delta x as delta x approaches 0, and now this delta x and this delta x will cancel out, leaving just 1 by x. So that's the derivative of log x. If you remember the log x function, it kind of goes up and then it slopes. So what's happening is that initially the derivative, which is the slope, rate of change of log x with x, was steep, it was large in magnitude, and as it goes up, it starts falling and it gets smaller, and that's what also this particular closed form solution is telling you, that as x gets larger, the derivative gets smaller and smaller. Log x is actually the slowest increasing function. So I'm going to just once more discuss limits in calculus. So the way it is written is, for example, you have the derivative to be defined as the ratio of changes in the function and the independent variable when the change in the independent variable delta x was approaching 0. Right? So this is by definition the derivative is defined as this when the change in the independent variable delta x approaches 0. And then from here you come to this equation where you basically this has cancelled out with this, and delta x squared you divide by delta x, you have only delta x left. So you had as delta x approaches 0, 2x plus delta x. And once you have this expression, you say, okay, now 2x plus delta x as delta x approaches 0, you remove this limit sign and then you just eliminate this delta x here, and you say that is equal to 2x. So the question which may occur is it that delta x equal to 0? I mean, when we just eliminate this delta x, and the answer is no, because if it was 0, then we could not have done this cancellation, because division by 0 is not allowed. So is it that the equality sign is not correct? And the answer is no, actually the equality sign is correct. However, here on the left hand side, you still have this limit which has not yet been applied, delta x approaches 0, and once you apply that limit, then you can ignore this delta x and make it go away, and you're only left with 2x. So if this kind of seems to be a bit not completely correct, the answer is no, it is completely correct. You just need new axioms. So once you have the new axioms in mathematics, this entire thing is satisfactory and correct, and these axioms were developed by Cauchy and Weierstrass, so that's limits, and it's necessary for both integral calculus and differential calculus to work, and it represents a new development in mathematics over the pre-calculus mathematics. Now we are going to look at 4 things which are true about derivatives. The first one is that the derivative of the sum of 2 functions is the sum of the individual derivatives of the 2 functions. So you have a function, for example, fx equal to gx plus hx, then the derivative of fx equals the derivative of gx plus the derivative of hx. For example, think that you have money in the total amount of money that you have is the sum of money that you have, let's say, in your checking account and your savings account. So the total amount of cash, if it equals the money in checking plus savings, then the rate of change of cash for you with time would be the rate of change in the checking account plus the rate of change in the savings account. Okay. So essentially, the rate of change of this function fx equals the rate of change of gx plus hx. Now, of course, money is a discrete, will usually be a discrete function with time. It will remain at a certain level, and then it will maybe go up by $100 or go down by $50. So the calculus actually applies only to continuous functions. That's a requirement. Otherwise, you could not apply limits. You could not have this idea of infinitely small changes. So, for example, what is in nature, what is continuous? Time is continuous, distance is continuous, amount of water in the bowl is continuous. These things can vary continuously. Population of a country is discrete. You can't have half a person or so on. So calculus strictly applies to continuous functions. And here we, this example I gave you, I'm just assuming, suppose it could be continuous, but generally money is something which will be discrete. The second thing that is true about derivatives is that if you have a function that is some constant into another function, so fx here is constant c into another function j, then the derivative of f with respect to x is c into the derivative of j with respect to x. Now this actually would follow from the previous, the very first thing that we did, where the derivative of a function which was the sum of two functions would be the sum of derivatives, because multiplication can be expressed in terms of addition. Just for example, think that, let's say, fx is the total amount of money raised for some charitable cause, and jx, like let's say there is a firm which says that, okay, whatever money you raise, we are going to match that money. So if you raise the amount jx, then the total money raised would be twice into jx, because whatever you raise would be matched by the firm. And then your derivative of fx, that is how fx would change, for example, with time, would be twice of how much money you're being able to raise. So the total money for the charitable cause would be twice the money that you are raising. Now we come to the third thing for derivatives. And here what we have is that if a function is the multiple of two functions, so for example here fx is the multiple of j x into kx, then the derivative of fx equals jx into the derivative of kx plus kx into the derivative of jx. If you wanted, you can actually prove this by first principles. You can treat that as an exercise. An example of application of this would be, suppose fx equal to x multiplied by log x, then the derivative of x with respect to x would be the first function, which is x, so or our jx here, the first function x into the derivative of the second function, that would be d log x by dx, plus the second function, which is log x, into the derivative of the first function, which is dx by dx. Dx by dx is simply 1, the rate of change of something with respect to itself. That ratio is always 1. And then that equals x into derivative of log x is 1 by x, so x into 1 by x plus log x into 1, and so that's simply log x, or that equals 1 plus log x. So the derivative of fx equal to x star log x is 1 plus log x. And this also means that if you wanted to integrate this, the integral of 1 plus log x dx would equal the function fx plus a constant c. So that was the, we had discussed earlier that integration and differentiation are reverse operations. So if you found that the integral of fx, if you found that the derivative of this x log x equaled 1 plus log x, then the integral of this will equal this plus a constant c. And the last of the 4 items for derivatives is the very important chain rule for functions of functions. Now, what's a function of a function? Well, a function is something which depends on something else. For example, when you're on the, when you're driving, the distance that you travel depends on time. So distance is a function of time, and there's something else which could depend on distance. So, for example, the amount of gas which your car is consuming could depend on the distance traveled. The amount of gas is a function of a function. And here's a second example. Now, here you have the air temperature T. Determines the rate of water evaporation for the lake mead, and water evaporation determines the level of water. So then your water level as a function of evaporation, if you say that's W as a function of rate of evaporation E, and then you say rate of evaporation is E, which is a function of temperature T, then water level becomes a function of temperature T as a function of a function. So we write a function of a function, the water level W equals, W is a function of evaporation rate, which is a function of the temperature. So we have W as a function of T, but it's a function of a function, and T, the temperature, determines rate of evaporation, which in turn determines W. So the question is, if I wanted to find how the water level was changing with air temperature, what the chain rule says is for a function of a function like this, the derivative is a multiple of the derivative of the first function with the second, like the derivative of W with E as the independent variable multiplied by the derivative of E with T as the independent variable. Now, this chain rule kind of like seems pretty obvious, because you think, okay, dW by dt equals dW by dE into dE by dt. So you can think that, okay, if I just cancel dE and dE here, I get dw by dt. But remember, these are not actually, this, even though it's written like this, this is not actually a division, because this itself is a function. And these derivatives are functions which have been defined in a particular way. They have been defined using limits, and they have been defined as the limit of delta x approaches 0, it is delta f by delta x. So even though they are written like this, they are actually not, this does not imply that you're dividing dw by dt. If that was there, then this chain rule would be trivial. It would not be anything that you would need to consider at all, but it is not. I mean, this is actually a function, this is a function, and this is a function. And this is just a representation for a particular function. So here we have an example of the application of the chain rule. We first say that f is a function of g. So f equals g squared. Next, we say that g is a function of x and g equal to log x. So then f becomes a function of a function x, a function of a function of x. So, what you have is fx equal to log x squared. Now, when you apply the chain rule, you want to find the derivative of fx. You can try doing it from first principles, but you already know the derivative of log x and the derivative of g squared. So you can use the chain rule to calculate the derivative of log x whole square by the chain rule. So what you would get is that df by dx equals df by dg, so the derivative of f with respect to g, into the derivative of g with respect to x. And derivative of f with respect to g, so the derivative of this function is simply 2g. And then the derivative of g with respect to x, where x is log x, is simply 1 by x. So what you have then is 2g into 1 by x, or substituting ln x for g, you have equal to 2 ln x by x. Okay, so that's the derivative of f with respect to x. Or if you are integrating this quantity ln x by x with respect to x, you would get the integral to be half of this quantity ln x squared plus some constant c, because if you have fx equal to ln x whole squared, then and the derivative of that is 2 ln x by x, then the derivative of ln x whole squared divided by 2 would be equal to ln x by x, and then the integral of ln x by x would become this quantity divided by 2. We are now going to take a look at some more examples of guessing closed form solutions for integrals, and we again go back to the equations for speed, which was 108 into t minus 27t squared. So distance is an integral of speed, that is to say that distance is speed multiplied by time, and because speed continuously varies, so you have to use integral instead of straightforward multiplication. So you represent the integral by this stylized s going from time equal to 0 to time equal to 4, and speed multiplied by an interval of time dt, and you take these little intervals of time from time going from t equal to 0 to 4, and that gives you the total distance traveled from time t equal to 0 to time t equal to 4. Now, what I would like to do is, I would like to save ourselves some trouble. I don't want us to have to like slice up that graph into little thin pieces and then add it up. Instead, I want to guess a solution. I could have plotted the graph. The graph looked like this. Once you give me the equation for speed, I can plot this graph and I can kind of slice it up into little tiny slivers and then add them. However, I don't want to do that. What I want to do is instead use calculus. And what I would like is that I would like to have an analytical solution to this integral, a closed, or what is also called a closed form solution. Now, if you look at this, then it is 108t minus 27t squared. So as there is this negative sign here, I can split this into two parts, like the integral of this and the integral minus the integral of this. So what is the integral of 108t? What function, if you take its derivative, gives you 108t? And the answer is it's 54t squared. You take the derivative of 54t squared, you just take the derivative of t squared, you get 2t, and then you multiply it by 54, you get 108. So the integral of 108t is 54t squared. Similarly, the integral of 27t squared is 9t cubed. If I take the derivative of 9t cubed, the derivative of t cubed is 3t squared, and I multiply that by 9, I get 27t squared. Hence, the closed form solution for this integral is 54t squared minus 9t cubed. And now I'm going to, I actually want to evaluate this integral between these two limits, t equal to 0 and t equal to 4. The way that is written is you draw a horizontal bar here, and then you say from 0 to 4. And then you stick the value of 4 into this, and then you subtract with the value of 0 in here. So if you stick the value of 4 into this, you get 54 into 16 minus 9 into 64 minus with the value here with the value with t equal to 0 in here. So minus 54 into 0 square minus 9 into 0 cube. So this actually is 0 at t equal to 0. So we just have to evaluate this, and this turns out to be 288. So the distance that you traveled from Los Angeles to Vegas is 288. The speed is something which varies continuously. It does not. It's not something which like goes discrete. You have this thing saying 0 to 60 in 7 seconds, or for a car. And the point basically is that it's not like 0 to 60 in 0 seconds. That would be a discontinuous function. So speed is something which varies continuously. So if you were to like describe it completely correctly, it would be a continuous function, and the continuous function you gave me was 108t minus 27t squared, and I found the integral for it, the closed form solution, And then I found that from t equal to 0 to 4, the distance traveled is 288. So now that you have a closed form solution, you can knock yourself out. You can find the distance traveled between any 2 points in time. For example, you say, okay, what is the distance traveled between 3/4 of an hour, so that's 0.75, and 3.2 hours. So into this closed form solution, you just substitute this number first, 3.2. So that will be 54 into 3.2 square minus 9 into 3.2 cube. And from that you subtract by substituting 0.75 into the closed form solution. So that will be minus 54 into 0.75 square minus 9 into 0.75 cube. And that equals 258.05 minus 26.58, or that's 231.47. So between the time 45 minutes from your start to the time 3 hours and 12 minutes, you would have traveled 231.47 miles. So this is kind of the power of closed form solutions. And of course, the real world is continuous or approximately continuous, and so we need closed form solutions. We need integral calculus rather than just trying to think of it as being discrete and making crude approximations. And so what about the volume of a sphere? Well, the volume of a sphere, we thought of a sphere as being composed of hollow shells which all stack up and make it solid, and each hollow shell is infinitely thin. So the surface area of each hollow shell, which is at a distance r from the center of the sphere, is pi r squared. So we assume we know what the surface area of a hollow shell is, and the volume of that would be the surface area multiplied by the thickness of that hollow shell, which is dr. And then the integral is between, now you want to find the volume of that entire sphere, so you start from the center r equal to 0 and you go all the way till the edge, till the surface of this entire sphere, and so you say that's capital R. So if the radius of the entire sphere is capital R, then your limits for your integral would be between 0 and capital R. Now, if you were to guess the integral for you want to guess what the integral for this is, and which is the same as finding a function whose derivative equals the function inside. So what is the function whose derivative will equal the function inside? Well, this is r squared. So how about 4 pi r cubed by 3? Now if you take the derivative of this, the 4 pi by 3 is a constant, right? So essentially you just need to take the derivative of r cubed and multiply that by 4 pi by 3. So the derivative of r cubed is 3r squared, and therefore 3r squared into 4 pi by 3 equals 4 pi r squared, which is the function in here. So the derivative of this equals a function in here. So this is then the integral of is this integral. Now this integral is to be evaluated for the volume of the sphere from radius r equal to 0 to the surface capital R. So according to our notation, you write it this way. You write first the closed form solution, and then you say r equal to 0 to r equal to capital R, and then r equal to capital R, you get 4 pi r cubed by 3, and then r equal to 0, you get 0. So this becomes then 4 pi r cubed by 3, which is the volume of a sphere. Now what about the closed form solution for the volume of a sphere? You have that to be 4/3 pi r cubed. So let's say if the radius was 2, then that will be 4 pi into 2 cubed divided by 3, or that will be 33.51. And because you have the, it's an integral between two limits. So this was if the lower limit was 0. So you were looking at the volume of the entire cube. However, you can also find the volume of a hollow cube, a hollow sphere by using this closed form solution. What is a hollow sphere? So it's like a sphere, and then inside there is a part of it missing. So here what you have is, what is the volume of a hollow sphere from r equal to 3 to r equal to 4? So that means that the inside part missing, this is 3, and the total is 4. So this is 1. I'm not like, the scale is not quite right here, but anyway. So that's the idea. It's a hollow sphere with the internal hollow having a radius of 3 and the external radius being 4. And then you substitute these numbers into the solution here. So you start with 4 pi r cubed by 3 with r equal to 4, and that is 256 pi by 3. From that you subtract 4 pi r cubed by 3 when r equal to 3, and that will be 108 pi by 3, or the volume of the hollow sphere will be 154.99. So we have seen one use of calculus, which is to calculate closed form solutions for, let's say, volumes or distances, etc. Another very important use of calculus is to find maximum points and minimum points of functions. Now, of course, in applied sciences, and if you think of economics also as an applied science, people are all the time wanting to find out maximas and minimas. They want to find what is the point of maximum utility, or what is the point of maximum profit for a firm, or they want to find, what is the point of minimum cost for a firm, or anything like minimum use of electricity for running some machine or something. So if you have functions, derivative differentiation can tell you, will give you a condition for maxima or minima. Now the idea is this. Now look at this function. Okay, so this function goes like this. Now, how about a point over here? Now then, if you look at this point and then you say that, okay, you have this idea of a tangent. A tangent is a straight line that just touches and lies along the curve at this point. Okay. Now, this tangent is the slope of this tangent equals the derivative of the function at this point. Now, why is that so? That is so because if you just look at this function here carefully, then over a very small range, the function is going like this, and the line which lies along it will just have the same slope as the function. And what is the slope of the function? Well, the slope of the function at this point is, if this is the change of along the y-axis dy, and this is the change along the x-axis dx, then the slope is defined as dy by dx. Okay, so what you would also note is that this is called a positive slope. It means that dy is increasing with dx. So you move in this direction along dx, and then y increases. So because the function is like this, so you have to, if you go this way, then the function has also increased. Similarly, at this point, the derivative is negative and the slope is negative. The function is on its way down. Okay, now why is the derivative negative? Well, here you can see the other way to think of it is that you see that here an increase in x, like let's say I'm moving from x here to x here, leads to a fall in y. Okay, so this dy is actually less than 0 when dx is greater than 0. And that means that the derivative is negative, and you can also use the word slope instead of derivative, and the slope is negative. So at this point the function derivative is positive, the function is increasing with x. At this point the function is decreasing with x. Now how about at the very tip? Okay, so this tip, what do you expect this slope to be? Well, at this very tip it's actually going to be flat. Now why is it going to be flat? Well, suppose it was like this, then I would say that, oh, that's not the tip then, because if I increase the x a bit, then y is also going to increase. Or if it was like this, I'll say that's not the peak either, that's not the very top either, because if I decrease x a bit, then y would increase. So the point at which y is at the very top, at its very maximum, it neither increases nor decreases when you move in either direction. So it does not increase if you move in either direction. And so this is the point of maximum. This is also the point where the slope and the derivative is flat, and you say, which is the same as saying the derivative is 0, because it means that when you move along the x-axis, there is no change in y. So basically the condition for maximum for this function is that the derivative be equal to 0. Okay. Similarly, if you had a minimum, so suppose you had a function like this for which you're trying to find the minimum, that also will have the condition that the derivative be equal to 0, because then it has to be flat also. And so how would you distinguish between the maximum and the, you just look at a function and you find that the derivative is 0, then how do you know if it's a point of maximum or a point of minimum? Well, one way you can do that is to look at the second derivative. Here, when it is a maximum, the slope started out positive and then slowly became 0 and then became negative. So here the second derivative is going to be negative because the slope starts out positive, goes to 0 and then becomes negative. So the first derivative is actually falling as we move along the x-axis, which means that the second derivative is negative. So the second derivative being negative is the condition for maxima. Similarly, the condition for a minima, you start out with a negative first derivative and then you fall to 0 and then goes positive. So the condition for a minima is that the second derivative is positive. So this is very useful. It's in applied sciences, and it is extremely it's a standard method for finding maximums and minimums, and that's what a lot of analysis is about. People want to know what is the best possible or the least bad, so stuff like that. So maxima and minima are very important things to find when you model in the applied sciences. So now I'm going to show you how to apply the criteria for finding a maxima or a minima to an actual equation or actual function that we have already encountered. The function that we encountered was the one you gave me for speed, and you said that speed st equaled 108 into time t minus 27 into t squared. So according to what I just described, if you were to take the derivative of it and set it equal to 0, it could either be for the maxima or minima. Now if I take the derivative of this, so it will be dst by dt. So that will be first the derivative of 108 star t, and the derivative of t is just 1. So this is just going to be 108 minus 27 star t squared. And as we did in our finding derivative by first principles, we know that the derivative of t squared is 2t. So this is going to become minus 54 into t. And if you set that equal to 0, it gives you that t equal to 2. So the t equal to 2 is either a maxima or a minima at time equal to 2 hours. That's when your speed reaches either a maxima or minima. And if to find like actually whether it was a maxima or a minima, we know it's a maxima. We know that you're kind of speeding and then you kind of started slowing down. So we know that it's a maxima, but I'm just going to show you what happens to the second derivative. Because remember, the criteria for maxima is that the second derivative must be negative. So if you take the second derivative of speed with respect to time, it will be d squared, it's represented as d squared st divided by dt squared. That's how you represent the derivative of a derivative. And there's nothing which says that you can't keep like taking as many derivatives as you wish. But the derivative of a quadratic, when you just differentiate it again and again, it's very soon going to become 0. But however, the second derivative is going to be, now this is going to be 108 is going to become 0 because the derivative of a constant is 0, and what you'll have left is minus 54. And this minus 54 you can see is negative. The second derivative is negative, which tells us that the point at which the first derivative was 0 is a point of maxima. Now the second derivative is always negative for this function. Sometimes you may have the second derivative also dependent on the function. Then you have to like substitute in the value of t that you have, like for example t equal to 2, and you substitute that into the derivative for the function for the second derivative, and then evaluate that. And again, if that's negative, it would be a maxima, point of maxima. If it's positive, it's a point of minima. Sometimes in some functions, you may get the second derivative to be 0. For example, if you take the function y equal to x cubed, the graph of the function looks something like this. Okay, so now the first derivative is 0 at x equal to 0, because the first derivative is just 3x squared, and that is 0 when x is 0. The second derivative will be 6x. And what is 6? Dy by dx for this function equal to 3x squared. What is d squared y by dx squared? And that's the second derivative. That is going to be 3 into the derivative of x squared, so that is 2x. 3 into 2x, that's 6x. Now this is 0 at x equal to 0. What about the second derivative? The second derivative is actually also 0 at x equal to 0. So this point here, you can see that the function kind of has paused and then it starts climbing again. So when you come from here, it's climbing, 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 pauses, and then starts climbing again. And so this actually, even though the first derivative is 0, it's actually neither a point of maxima nor minima. So just the first derivative being 0 does not imply that it has to be a maxima or minima. Most usually it is. However, if it is a point of maxima or minima, then it does imply that the derivative must be 0. The first derivative must be 0.